University of Hawaii. And I've seen him give presentations, and maybe it's doing up his work with the Hawaii Scientific Drilling Project that was out in Kilauea, some really interesting work. And he's currently the director for the Center for Study of Active Volcanoes, and he's been the director of that center since 1995. So it's great to have you here, and we look forward to your
Thank you. Good afternoon. What I thought I would do today is I'll give a summary of work that is currently underway. But I thought it would be also a useful opportunity to take a somewhat broader look at really the interaction or the relationship between the geology of Hawaii and Hawaii's geothermal resources. Given some of the statements that I've seen made in the news media, it's pretty clear that there isn't really a clear understanding of the resources and the geology and how those processes sort of interface with each other. So a good piece of my talk this morning or this afternoon will really be a bit of Hawaiian geology 101. And I hope you'll find it interesting. So I'll be talking about the geology of Hawaii's volcanoes, their formation and evolution, their geological structures, which are extremely important for the geothermal resources, the thermal structure and the evolution to the extent that we know it. I'll talk very briefly about some of the early geothermal studies that we did, the early assessments of potential geothermal resources in the state, and then talk about the work that's currently underway with a focus on the technology that we're using, how that works, some of the early results, and what our expected outcome would be. So, first question that we have to ask is, how do Hawaii's volcanoes form? How did we get here? Okay. Everyone here, I'm sure, is aware. I mean, we have the 5 major islands. They form a chain. Virtually everyone is familiar with that, but not everyone is aware that these 5 major islands are actually the end of a very, very long chain of islands that extend all the way up here to the Aleutian Trench. And when I actually started many years ago in the field of geology, it was really very much of a mystery, sort of what this feature was, what it represented, and in fact, they're still arguing about all of that. In the early work that was done, though, it was actually, I have to say, it was first recognized by the native Hawaiian people, that there was an age sequence to these volcanoes. If you go and look at the creation chant, it speaks of Pele coming to Hawaii and going first to Kauai and trying to dig a home with the Indian state, and being flooded out on Kauai and then moving to Oahu and progressively moving down to the Big Island, and ultimately establishing her home here at Kilauea. And that, what we Westerners call myth, was really a representation of the recognition that the age of volcanism in Hawaii progresses from older volcanoes here down to the younger volcanoes. And I like to point out to my students that the first Westerners that came here with their advanced technology said, oh, the Big Island must be the oldest because it's the biggest and it's had more volcanoes. Actually, the original Hawaiians had it right, the Westerners had it wrong. But as we researched the ages of these volcanoes, we were able to get estimates of how old, at least the surface flows of the volcanoes were. And Kilauea, of course, is quite young. The youngest flows are minutes old. We're still trying to sort out exactly how old when Kilauea started. We're estimating somewhere in the range of 400,000 years, more or less. I don't know, Jim, you may want to dispute that, but it is a relatively young volcano. Up here to Kauai, where the age is somewhere in excess of 5 million years old. And so whatever process is going on here at Kilauea has clearly been going on for at least 5 million years, and we can actually chase these islands all the way up to Meiji Seamount, where the age is on the order of about 75 million years. So the process that produced Hawaii Island has been going on for at least 75 million years, perhaps longer, because any older volcanoes have already gone down the chute into the ocean trench. So at least that long, we know this process is going on. And in today's debate, there is a general model that's referred to as the mantle plume model. And it says that we have a plume of material that's rising. Some of us believe maybe originating near the core mantle boundary, rising up under the lithosphere, where we get partial melting of this rising material, and that actually is our magma supply that is coming up and feeding not only Loihi Seamount, which is the youngest of our active volcanoes, but also Kilauea and Mauna Loa. And as time progresses, the Big Island will eventually move off of that mantle plume, and the volcanoes that are currently active will go through the same process that Maui, Molokai, and Oahu has, where there will be a gradual waning of volcanic activity. And in fact, this is also a very little known fact, the youngest eruption on Oahu is only 30,000 years old. So this volcanism will continue for quite a long time. So, let's talk about the Big Island specifically. Kohala is the oldest volcano, and sort of our image of the volcano, the way that we often look at it is, okay, well, this is Kohala, this is Mauna Kea, Kualoa, Mauna Loa, and Kilauea. In actual point of fact, these volcanoes didn't look like this many years ago, and even actually I have to confess that even this sort of hypothetical picture of the island 600,000 years ago is probably inaccurate. Kohala volcano was considerably larger than it is today. Mauna Kea was about, or just slightly higher than Kilauea. Mauna Loa was just barely breaking the ocean surface. My point here is that these volcanoes are actually growing. Each volcano has grown onto the flank of its older sister volcano. We believe the sequence was something on the order of Kohala. There's another volcano out here that is called Mahukona, which is actually below sea level, but did contribute at one time to the Big Island. Hualalai, though, was the next major volcano that formed Kea, Mauna Loa, and then, of course, Kilauea and Loihi Seamount will eventually grow to attach itself to the Big Island. But another process that goes on here is that as these volcanoes are growing, they're also loading the Pacific plate and pushing it downward. So as the volcanoes are growing, they're also sinking. And again, being overrun. So when we look at, say, Mauna Kea extends some distance out here under the flank of Mauna Loa. And we learned this in our drilling that we did at Cape Kaha. We started drilling down here, and the flows that we started drilling into were Mauna Loa flows. And we had 1,000 feet of Mauna Loa flows before we hit Mauna Kea. And then we were in Mauna Kea pretty much the rest of the drilling. One of the interesting features that we're only now coming to grips with, though, is that Kohala volcano, we sort of assumed was relatively small until we did some dredging out here on what we thought was the east rip zone of Mauna Kea. And it turns out that the lavas here look more like Kohala than they do Mauna Kea. So Mauna Kea is actually built on a much larger Kohala volcano than we had previously recognized. Now let's talk a little bit about the structure of the volcanoes. This is sort of a cartoon, one of many that you will find of a continental volcano. where you have a conduit coming up to the surface from some sort of unspecified magma chamber, and this magma rises up, it erupts at the surface, and builds this stratovolcano. Hawaii's volcanoes are not built in exactly that way. The Mount St. Helens, the Mount Adams, the Cascade volcanoes are built on the continental plate. Hawaii's volcanoes are built on the Pacific plate. So we look at Mauna Loa, 13,000 plus feet high. Well, no, that's not correct. Mauna Loa is actually something approaching 30,000 or more feet high, because the ocean depths here are another 15,000 feet down. So we have to look at these mountains as basically extending from the ocean floor up to their elevation above sea level. And they make the Mount St. Helens and the Cascades volcanoes look a bit like pipsqueaks. They are, in terms of mass, much, much larger. And again, this is somewhat speculative, but our ideas of how these volcanoes grow is that they start out like Loihi Seamount, a relatively steep-sided volcanic edifice made up of pillow lavas. As that edifice grows and makes it to the ocean surface, we see very active explosive activity, and then eventually we get a shield stage of activity and late stage eruptions where the chemistry of the lava changes, and we go from a Mauna Loa looking shield to a more peaked shape similar to Mauna Kea. Now, my point in putting this up here, though, is to point out that most of, or virtually all of, the erupted material that comes out of a volcano is cold within hours to days of the time that it's erupted. And that makes up the vast majority of the volume of Hawaiian volcanoes, is the erupted volume. I saw recently a comment that, oh, well, we could develop geothermal anywhere. Totally untrue. There are only specific structures within these volcanoes where heat is stored underground. And we actually can say with absolute certainty that there is not universal heat. We drilled this deep hole at Keaukaha, and we went down 11,500 feet. Temperature of the water coming out of that hole was maybe warm enough to take a bath in. The temperatures were not very hot. And that basically, in that hole at the thermal gradient that we were seeing there, we would have had to drill about 20,000 feet in order to hit the boiling point in that well. So the idea that we can just go punch a hole anywhere and develop a geothermal resource is really not based in reality. Anyway, these are other cartoons of different types of volcanoes in the continental environment. Hawaii's volcanoes are very, very different. They do have a characteristic structure, and they're a bit different from a lot of the other island volcanoes as well. There is that central conduit here, and this conduit, okay, you'll notice here on this side, this is the depth in kilometers. The source material for the lavas that come to the surface is 25 to 40 to 50 kilometers down. So the ultimate source of the lavas coming into the volcanic system is quite deep. The volcanic shield may start anywhere from 8 to 10 kilometers below the ground surface, or below sea level. As these volcanoes form, let me see if I can back up just 1 second. You'll notice this feature here in the shallow environment. Okay, this is termed the rift zone. Okay, the rift zone is a zone of weakness within the volcano where magma coming up into this conduit, there is a magma reservoir. We're still trying to get a handle on what the size of that reservoir is and how that size may evolve in time. You can look at the summit of Kilauea and see the caldera there, very active. It has had magma below that caldera at some time in its past. but that magma chamber is a variable size, but it's relatively weak, and magma is able to travel out underground through the flanks of the volcano. And it turns out, or it's been estimated, I should say, that as much as 55% of the magma that comes up into the summit reservoir of Kilauea actually gets drained off into the East Rift Zone. These are major features of virtually all of Hawaii's volcanoes. And it's interesting to note, okay, here, if you can see it, this isn't a great image, but this is Loihi Seamount here. And Loihi Seamount is still 3,000 feet below the surface, but it also has a caldera and rift zones. So this structural feature of Hawaiian volcanoes seems to start at the really very beginning of the formation of the volcanoes. And it turns out Kilauea East Rift Zone here extends about 30 kilometers above sea level, but another 30 kilometers below sea level. It extends all the way down to the ocean floor. And what is also evident is that some rift zones are bigger than others. The Southwest Rift Zone, for whatever reason, perhaps I'll speculate and say perhaps because of the formation of Loihi here, it has sort of helped stabilize this flank of Kilauea so that that Southwest Rift Zone is not able to accept as much magma as the East Rift. And as many of us who've been around for a while know that the East Rift of Kilauea is extremely unstable. If you were here in 1975, you would have experienced in 1975, what was the magnitude, Jim? 7.6, 7.8 earthquake? Very significant earthquake, shook the whole state. But this flank of Kilauea is in a state of sort of episodic failure. And that episodic failure allows magma to be injected into this rift zone. Mauna Loa, we have a northeast rift zone and a southwest rift that extends also down to the ocean floor, to Waialae. Mauna Kea, and this is an old image, this is probably incorrect. There is unlikely to be a east rift zone of Mauna Kea. There is actually new data indicates that there may be a southeast rift zone there. But it's within these rift zones that magma is injected underground, and that magma then will slowly cool and crystallize. And it's only in those locations that heat is being stored within the volcano. And so, drilled here in Hilo, no heat at all. We drill over here, perhaps no heat at all. So, one other feature of these rift zones is that they're somewhat mobile. This is an old image of a cross-section through the Kilauea East Rift Zone. And that rift zone, we believe, over time has gradually moved to the southward as the south flank of Kilauea has failed. So the active portion of the rift zone is actually only a relatively small part of it. And we can see that active portion because this is where the lava flows come from. We believe that perhaps at one time in the past, the East Rift Zone looked like this. But that older rift zone is now buried by hundreds to thousands of meters of more recent lava flows. And we really don't see any evidence here of additional heat. The activity within the East Rift Zone is also marked, though, by high temperature wells. There have been a number of deep wells that are drilled, but even before those were drilled, there were shallow water test wells that included what I knew at the time as the airstrip well. There is a Malama Key well here. There is an old test well that was drilled in 1962, the Geothermal Test Well 3, a couple of test wells, shallow test wells here and here. All of those wells encountered warm water within the East Rift Zone. So there was active leakage of hydrothermal fluids coming up into the water table at least as early as 1975. And in fact, I was told by the old timers that there used to be some hot ponds down here that Jack's Tours, they had basically a spa and resort kind of a system going down here where the tourists would go soak in the hot volcanic water. I guess it was the 1960 eruption that that wipe those out. But anyway, we know that there is active heat within this rift zone. Now, our current view of the rift zones, though, is that Komohana volcano probably has a rift system that extends out into this Hilo ridge. Mauna Kea, we're not quite sure where this west rift system goes. There appears to be a southeast rift. Mauna Loa has actually, it's believed by some at least, a fossil rift zone that comes down through the Nowelo Hills as well as the currently active portion of the rift. Of course, the Kilauea East Rift here, Hualalai is believed to have a rift system in here. There were also reports of intrusion out in this region back, let's see, I believe in the 20s. I've lost that date, but anyway, quite a number of years ago, there was a flurry of seismic activity up north of Hualalai that some have attributed to an intrusive in the area. But it's those areas that we're interested in as potential geothermal resources within the state. And again, an image of the whole chain. We go up here to Haleakala, and this gives you a good perspective on the Haleakala East Rift Zone. It also has a southwest rift. One thing I wanted to note here is that you look at Kilauea, and you can see this very sharp slope change that reflects the transition from subaerial lava flows, from the growth of the volcano above sea level to the submarine slope. That's a very sharp break. But we can see here that that break is offshore quite a ways. What this is telling us is that at one time this was above sea level, but Mauna Kea and Komohana volcanoes have subsided their original mass below sea level. The same is true, and I'll show you some more detailed images of Maui and Oahu. So at one time, these islands were actually much bigger than what we see above sea level today. Again, you can see that shelf here was at one time above sea level. And you can also see the slope break down here, which is the Mauna Kea.
So, Don, what you're saying with that is that the undersea, when it pours on lava undersea, it forms this steeper thing, when it's above ground, it forms above sea level.
Right,
it's
right.
flatter.
Yes, and the reason for that, of course, is that when you're dumping lava flows into the ocean, they chill much, much faster. They can travel much, much shorter distances, whereas above sea level, the cooling is much slower and they can travel much further. And in fact, sort of the implications of that is that much of the material underlying these slopes is actually fragmental material that was created when lava flows went into the ocean. And so there isn't an awful lot of solid, what would have been solid pillow lava under there because of the way that the volcanoes grow. So for Maui, and I'm not sure if I've got a good image of Maui Nui, but actually Maui Nui, this was at one time above sea level, and actually what we call Maui Nui was Maui, Molokai, and Lanai were all part of one island. At least that's the conjecture. But this Haleakala East Rift Zone extends at least as far down to the ocean floor as the Kilauea East Rift Zone, and clearly has high potential for there to have been heat deposited within that rift zone. The southwest rift zone is also of interest because it's also believed to have been most recently active of Haleakala's rifts. And Oahu, we're not completely discounting it in spite of the age, and this is a point I need to make, is the older these volcanoes get, the more time has passed to allow this heat to dissipate. And this is really one of the major outstanding questions that this study is intending to try to resolve, is how fast does this store of heat that is underground as part of this cooling magnet, how long does that last? We really don't know. We can make some conjecture. Let me just mention this very briefly. We do know in our previous work that there's actually warm water coming off of West Maui. There are some shallow wells here along the Oahu Canyon where the water temperature is about 33 to 35 degrees Celsius, clearly above ambient. So that argues that there is heat that is stored for a significant period of time. Oahu, the story is a little bit different. It turns out that this is the caldera region of the Kilauea volcano, and that's the younger of the two volcanoes on Oahu. And this is the caldera region of the Waianae volcano. What's interesting here geologically is that if you look on the Big Island, the caldera is usually kind of in the middle of the volcano, whether it's along a linear feature or a round feature. So we can legitimately ask what happened to the rest of Kilauea and Waianae, and the answer is right here. The Kilauea volcano has been virtually bisected. If any of you visited Oahu, you see those very steep cliffs on the northeast flank of Oahu. That is due to this major landsliding event that took away a significant fraction of the Kilauea volcano. And apparently the same thing also happened with the Waianae volcano as well. So the caldera regions, though, look to be, if there is to be heat stored on Oahu, then we would expect it to be within these calderas because, again, that was the magmatic conduit and where the largest majority of the heat would be stored. So, bottom line, take-home message is that okay, the geothermal resource isn't everywhere. It's in specific geologic structures that we have looked at in a somewhat cursory manner in the past, and we're going to be looking at in much more detail in the future. So in the early work, and we did a statewide geothermal resource assessment in about 1983, and in that we pulled together as much geologic data as we could. We looked at those geologic structures and identified where those structures were, what their ages were, and used that as part of our inference on whether there was likely to be a resource there or not. I'd point out, too, that in 1983, the picture of drift zones was very much different than it is today. So we still have quite a bit to learn about really even these internal structures that supposedly are going to host the geothermal resource. So we also looked at the age of the most recent activity. We looked for evidence of ongoing activity. And as I mentioned, the Kilauea East Drift Zone, abundant evidence of active hydrothermal discharges of groundwater being altered, chemistry being altered, and discharging into the shallow water table. So we looked at the subsurface temperatures, we looked at the chemistry of the groundwaters, and we did find evidence of chemical alterations in some of those Maui wells. We also found some evidence of anomalous water chemistry, even in the Waianae caldera. So, these were somewhat positive evidence, and we did some very limited geophysical surveys. But 1983 is 30 years ago, and there have been substantial advances in geophysical survey techniques since that time. But that original data we used to generate these maps that have been sort of passed back and forth. Of course, the Kilauea East Drift Zone, we estimated a modest 95% probability because we knew that there was a resource there. Perhaps extending off somewhat to the north. Maybe you note that even the Pahoa well shows some evidence of geothermal water in the drinking water well there in Pahoa town. On the Mauna Loa Southwest Rift, given its recent activity, we felt that there was a high likelihood. At the time, we did not have any water chemistry data or temperature data, but since that time, the well that was drilled down here for Hawaii Ocean View Estates reportedly did encounter elevated temperatures. So There is apparently some leakage of thermal water coming off of the Mauna Loa Southwest Rift. The Mauna Loa Northeast Rift Zone, we limited the potential area up here at to the high elevations, because this rift zone seems to disappear as we move further to the east. There's just really no evidence of recent activity, excuse me, and we don't know when the last intrusion has gone into that rift zone, but it could have been a substantial period of time. We had virtually no data from Mauna Kea, neither water chemistry data nor temperature data, and we didn't even really have a good fix on the rift zones there. So we really just took a pass on Mauna Kea. Ko'alalai, there was actually some geophysical work done by the staff of the USGS. I guess it was in the 70s. Dallas Jackson and others did some spontaneous potential surveys up there. Spontaneous potential I'll talk about here in a little bit, but it's a geophysical technique that actually can identify water flow and steam flow in the subsurface, and they did find some evidence that there was some activity within the Ko'alalai rift zone. But we gave that, I believe, a 25 to 35% probability. And actually, I should mention that subsequently some wells drilled down here on the flank of Ko'alalai have come up with distinctly anomalous fluid chemistry. So actually, today's data, I would probably increase that probability somewhat. On Maui, we gave about a 25% probability, but that was based almost entirely on the sort of geologic history of Paumacoa. We didn't feel we had enough data to make an assessment on West Maui. As I mentioned, we do have warm water there. And Oahu, I believe actually in our reports we gave about a 5% probability for a low temperature resource in the Waianae caldera, and I believe we did not have enough data to even make an estimate in the Ko'alalai. But again, the techniques that we had available to us were fairly primitive, and we really could not get a good look to depth where, if there is a resource, it's likely to be. So really the work that we're undertaking right now is a reevaluation using modern exploration methods. And the primary method we're going to be using is magnetotelluric surveys. Kind of a fancy term, and it's actually a fairly esoteric technique. I've had, depending on what generation individuals are from, they describe it as either Buck Rogers or Star Wars. But it takes advantage of this idea. Okay, if you're familiar with radio waves, okay, you've got a transmitter that generates radio waves. If you have a conductor that is tuned to the right frequency, that antenna can receive those waves. It can pick up those waves. That's how your television used to work. It's now a digital signal. That's how your radio used to work. I think it's now digital. But it still depends on these electromagnetic waves. And there's all kinds of man-made waves. Okay, we've got transmitters for FM radio, TV, AM, et cetera, et cetera. But turns out there's also naturally occurring radio waves or electromagnetic waves. These waves actually pass through the ionosphere. They are generated or stimulated by lightning that occurs mostly in the tropical environment. But as the lightning occurs, it sends a pulse of energy up into the ionosphere, and that energy basically circulates around in what I believe is called a ring current. We also have electromagnetic waves generated in what we call the heliosphere. Okay, this is in the very far outer envelope of atmosphere for the Earth's surface, and is generated by interaction of the solar wind with ionized particles in the outer atmosphere. These are important because both the ionospheric radio signals and the heliospheric signals have a very broad spectrum and have a very, very long wavelength component to them. Why is that long wavelength important? It's important because short wavelengths are attenuated very quickly when they pass into the Earth. Long wavelengths, and we're talking about periods of thousands of seconds. Okay, we're accustomed to talking about radio waves as thousands of cycles per second. We're interested in radio waves that are thousands of seconds per cycle. And these waves can penetrate to depths of 100 kilometers into the Earth. And when they interact with a conductor in the Earth, we can tell that by sensing these signals at the Earth's surface. And that's what we're after. With that, and it's lots and lots of computer processing of the signals that we receive, and I'll talk about how we go about collecting these signals. Those signals, as they interact with conductive zones in the Earth, we are able to map those conductive zones. And we can map them down to 10 kilometers or more below each of our stations. And that electrical conductivity is tied to the rock type, also tied to the temperature of the rocks, and to water saturation in the rocks. So we've developed the capability, or we're in the process as well of developing the capability to also map fluid flow. I'll talk a bit more about that in a minute. So the mechanics of the surveys are relatively low impact. Essentially, these are the antennas that we use to receive those incoming signals as they interact with the conductive zones in the Earth. Okay, they're buried roughly a foot deep into the ground. And we have electrodes that are actually sensing the electrical voltage of the ground. And we record those two signals simultaneously for a period of about 5 days for each station that we have out in the field. We have applied the technology to groundwater exploration. We've done it over the saddle. We've done surveys across the saddle region where we installed a sequence of stations extending from what is called the Saddle Road well, which is the highest elevation water well in the saddle, all the way across almost to the Momoa Highway. In that effort, what we were doing was trying to map the groundwater system within the island. And basically, we were able to map the electrical conductivity of the Mauna Kea flank down to sea level. And this is what sort of the outcome looks like. These colors are representative of the electrical resistance of the rocks. The warm colors mean that the rock is very highly resistive. And in this study, basically this very resistive rock tells us that this is dry stuff, because we know that dry rock is way more resistive than wet rock. Now, as I mentioned, we started down here at this KM01 site, and that's where we have an existing well. We know that well has water at about 1,000 feet above sea level. And the resistivity of that Mauna Kea basalt was around 600 to 700. The terminology used in the technology is ohm meters. 600 to 700 ohm meters is the resistance of the rock saturated with fresh water. And so what we did is we went across the saddle looking for areas in which we found that 600 to 700 ohm meters. And what we found was that there is a region, this location is about where the Mauna Kea Observatory Access Road takes off from the Saddle Road. And so just to the east of that, it looks like we have water that may be as much as 1,000 meters above sea level. Likewise, further to the west, we find another area in here where it appears that we may have freshwater saturated rocks about 1,000 meters above sea level. Now, this is significant in another context because our existing models for groundwater have always predicted that, well, you know, you're only going to find fresh water rising to a few tens to a few hundred feet above sea level in the interior of the volcanoes because the rock is so porous and permeable. That water runs out and discharges as coastal springs very rapidly. And so this is fundamentally new information saying, oh, these volcanoes are storing much more water than our earlier models had anticipated. And in fact, what I'm doing right now is we're drilling a test hole in that latter region to see where, in fact, the water table actually does stand. So the geophysics, and this is something that Jim will appreciate my saying, is the geophysics will always tell you maybe. That low resistivity can be one of a number of things. Optimistically, it's water, high-level water. It could also be a different type of rock. It could be something else that we haven't thought of. And so the only way we can really prove it is by going in and taking a look, and that's what we're doing. Anyway, we were able to map that electrical conductivity all the way across, and again, it's tied to the rock type and the dikes, that very highly resistive zone there. That probably was very dense rock, intrusive rock, associated with the Mauna Kea Southeast Rift. Because that's extremely high resistivity for typical flow of soil. But it's also tied to the level of saturation and the salinity of the water involved. And this is kind of a cartoon of what we found here, this Mauna Kea dike complex here. Perhaps we're looking at ash beds that have influenced the movement of water through the flank of Mauna Kea. We're not sure. This is pure speculation at this point, and that's why we're drilling the hole. This same technique has been used, though, in places like the Cascades. This is Mount St. Helens, Mount Adams. You can see, again, in this case, the electrical resistance is reversed from the other image. The very warm colors are very low resistivity, and this likely correlates with the hydrothermal system and or a magma chamber below Mount St. Helens. So we know this technology can work. In terms of looking, I can tell I'm fouled up on this. In addition to looking at the electrical resistivity, we're going to be looking at a technique we're calling spontaneous potential, where we are looking at a different phenomenon, and it's based on fluid movement through the ground. Turns out that fluid movement in rocks is like a battery. You have water passing through a rock. Some of the elements, some of the ions dissolved in that water actually stick to the rock stronger than others, and you get a charge separation. That sets up a current. So we will be looking at the spontaneous potential generated by that subsurface flow. And actually the purpose of that is to identify areas where there may be permeability. If we do identify a hydrothermal system, we look into that hydrothermal system and see where fluid flow is occurring. Okay, this is actually an application where they've got leakage through a dam, and it shows up very clearly in the spontaneous potential. As I mentioned, the work that Dallas Jackson and others did on Nowelo St also found that. Okay, and this is spontaneous potential around Ijin volcano in Java, and shows very strong hydrothermal potentials over on this side and water flow downward over on the other side. So it gives us an idea of fluid movement within the subsurface. And these are the techniques that we're going to apply. So the work that's currently underway, we've been working up at the Kilauea summit. And the purpose of that is to go into an area where we have known hydrothermal activity and where we have known changes in hydrothermal activity associated with volcanic activity going on within the summit caldera, and use that as sort of a ground truth for the technique when we take it to other locations. And we put in something like 20 stations around, this is Halimama, but both in close proximity to Halimama as well as well removed. And one of the most interesting pieces of data that may not look terribly interesting to the average layman is that we have this set of stations, 7, 8, 9, and 11. And let's see, 11, 8, 9, where is 7?
At the bottom.
7, right there. This was one day, this was the next day, and you can see this was station like number 9, shows a substantial change. The day-to-day difference was that this was during a deflation-inflation event, where magma, in this case, was moving underground. And it does show us very clearly a change in the SP, in the spontaneous potential. So we do believe that we'll be able to see these kinds of effects within the hydrothermal systems as well. And as most research projects go, we had hoped to be much further along by now than we are, but we found that there will be some challenges in getting this data and getting the instruments calibrated, but they do seem to be extraordinarily sensitive. And I think if there's any way that we're going to get useful data on hydrothermal systems on the older volcanoes, this is how we're going to do it. We're basically going to continue this work, continue the ground truth work in Puna, do some transects across the East Rift Zone where we have known hydrothermal activity and known fluid flow, and then we'll look at the Mauka, Mauna and Huala Rift Zones on this island, look at the rift zones on Maui, and we'll be looking in the caldera areas on Oahu. But that is sort of the plan at this point. I guess our priorities are actually over here on the west side. Once we finish in the Puna area, see if we can identify any evidence of activity here on the western flank of Mauna Kea, on the western flank of Huala, and we're going to actually reserve Mauna Loa for later studies. If we can find something over here, I think basically the Big Island will certainly have as many potential resources as we're likely to need to look at any time in the near future. We're very interested in looking over here on the west flank of Haleakala, because again, with this huge rift zone extending out here, we're expecting that there would have been very substantial quantities of magma injected underground here, and that may be the largest store of heat within Haleakala. Although we may also be looking over here as well, really depending on the timing of things. And then again, Oahu, we'd be looking back here in the Kapa'a Quarry area. That Kapa'a Quarry is actually quarrying part of the old dike complex of the Kilauea volcano. And if there is any heat stored within that complex, then we should be able to find it there and in the Waianae caldera. Those are the primary targets. Our expected time frame, we're hoping to have our field surveys on this island completed by the end of this year, and probably be at least another 6 months of data processing before we have all of that data processed. This is only about really 10% of the effort is the field work. The other 90% is the data processing, the data modeling, and that traditionally takes quite a long time. Maui, we hope to have the field work completed by mid-year, and Oahu complete mid-year to late next year, somewhere in that time frame. But that's sort of our planned trajectory, and by then I hope to be able to answer really the fundamental question of how long do these hydrothermal resources last, how quickly do they lose their heat through natural processes, and are there viable resources on the older islands? And I think that's the last slide. I'll be happy to answer questions. Thank you very much.
Yes. On your picture
line flow on one side of the crater ductflow, how do you determine which direction it flows?
One is positive, the other, we see a positive potential on one and a negative potential on the other. And again, it's based on this idea that the flowing conduit is acting like a battery. And some ions are left behind and give you that charge separation. So that's how you can distinguish between upflow and downflow. Yes?
Maybe you kind of answered this already, but I've heard people say that the PGV resource is just cooling down gradually and that it'd be very difficult to find any others. What's your opinion on that?
Well, the work that we did in the late 80s and early 90s, we drilled the scientific observation holes, and they were at about 2 or 3 kilometer spacings along the strike of the rip zone. And we did 3 boreholes, and all 3 were quite hot. The one furthest to the east, the temperature was actually considerably hotter than what they're working with at Puma Geothermal Venture. I believe the temperatures were approaching about 700 degrees Fahrenheit. So there's really strong indication that along the strike of the rip zone, along the direction of the rift, that there is high temperature pretty much along the entire extent from that deep drill. And I think the geophysics would also tend to confirm that. Any questions? Yes, ma'am.
Given the technology that's available to you right now, what advice might you give to companies that would like to drill in the East Rift Zone for geothermal without access to your data? So basically to go in and drill semi-randomly.
Well, again, the way that I look at the Kilauea East Rift Zone, and the question has a lot of different aspects, different facets. The data that we have, I think, for my sense, is that the Kilauea East Rift Zone is a known geothermal resource. It is, there's heat there. There are other questions that need to be answered. Is there permeability in a specific location? But there's definitely heat down there. And what the hope is that this data will provide incentive to look in other locations on the island. And part of the impetus for that, okay, one, as we all know, I mean, the Kilauea East Rift Zone is lava flow hazard 1. There is a high lava flow hazard in that area. If we can put resource developments in a lower hazard area, that can be a good thing. But that has to be balanced again against whether there's heat in these other areas. That's what I'm trying to answer. Is there heat in these other areas that would make a viable resource, say, on Mauna Kea, on Nowelo, on Haleakala? Because we don't have the answer to that yet.
Can you determine the permeability from the surface or get a handle on it, or does that take a test well?
At this point, it takes a test well. We don't have a technique, and this is why, and I failed to mention this, the work that we're doing addressing the spontaneous potential is an effort to be able to estimate what the permeability is. If we have flow, if we can map that subsurface flow using a spontaneous potential, and this is something that has not been proven. If we can do that, then that's a good proxy for permeability. If you have flow, then you must have permeability. If you don't have flow, then you may not have permeability. And so this would, the overall intent is to reduce the dry holes, reduce the need for these, really almost blind exploratory holes, where even though you have heat, you may not have that permeability. And this is, again, let me digress for a second. I mean, in order to have a viable geothermal resource, you have to have heat, obviously. You have to have fluid present in the formation, or be able to get fluid into the formation. You have to have the permeability. You have to have the ability to move that fluid through the rock. And this is probably another common misconception that I can address here, is that the heat source is not the water. The heat source is the rock. The water is your medium for getting that heat out and making use of it. And if you don't have a mechanism for doing that, it's not a viable resource. So we're trying, and this is why the Department of Energy has funded a portion of this work, is to see if we can do this spontaneous potential survey and infer something, be able to infer something about the fluid flow at depth in the hydrothermal system. Because that really will be a major step forward in our ability to identify viable resources.
Now, what's the total cost of this program, and what kind of product, how high a confidence or detail are you going to be able to show at the end of the project?
Well, the overall cost is, we have about $1 million in funding from Department of Energy, and a little bit less than that has been made available to us through the state. And we hope to get data, and this is a research project. I can't guarantee an outcome. We will do surveys over these rift zones in at least a high enough density to be able to say, okay, there is a high probability of heat, or there is not a high probability of heat within this region of the rift zone. We're not going to do a tremendously dense survey that you would typically use to site a well, because that's not our purpose. If we find an area that looks promising, I mean, all that information will eventually be public. It really depends on state land. The data and interpretations are public immediately. In private lands, basically, in order to get access, we have to give the landowner first rights to that data. If they say, no, you can't come on my land and do surveys, then we get no information. So we do have to sort of come to an agreement with the private property owners to allow us to get access to that land. But DOE's policy is that, if that data is not ever going to be public, then you're not going to go there. So that's going to be part of the negotiation. But the intent is to get enough data to say there is a reasonable likelihood that we have subsurface heat within this region, and if you're interested in that heat, then maybe you should go in and do your own surveys at higher density and make your own decision. But the idea really is not to give a final answer, but to stimulate interest where interest is warranted in an area that may have subsurface heat. Yes.
You talked about the high seismic activity in the Pacific zone, and you cited a 7.6 or 7.8 earthquake. Probably have potential for even larger earthquakes. And then you were talking about episodic failure, I think, on Oahu, where the counters.
No, the failure on Oahu was basically a collapse of the seaward flank of Komohana volcano and of the seaward flank of the Waianae volcano.
So I thought I heard you saying that Kilauea, the East Rift Zone of Kilauea was maybe
It's, all the flanks of the volcanoes have the potential to slide off. All of the islands have experienced, landslides of one form or another.
So what do you think about changing the pressure balances in the seismically active area like Kilauea? Like, just as an example, PGV reinjects 4.2 million gallons of brine a day. That seems substantial to us. Is there a potential there to induce some kind of seismic activity?
Given that Kilauea is periodically injecting magma into the East Rift Zone on a regular basis, of substantially larger volumes, I think what PGV, there's a couple of things. PGV is putting fluid back that came out of there originally. And what they're putting back is really a very small fraction of what goes on in the East Rift Zone on a routine basis.
So what would the effect be if we do get a really large earthquake? I mean, is that on PGV or any of the resources there? I mean, if you say you had an 8 earthquake, what do you think is going to happen?
I think it would be unpleasant for all of us. Certainly there has been a magnitude 7.9 earthquake on Mauna Loa, the 1868 event. These events, and I think we all have to recognize that the whole island is subject to these major events. I don't think that reinjection of geothermal fluids has a significant likelihood of generating one of those events. They do not happen frequently. There have been many smaller earthquakes on the East Rift Zone. Typically one every 10 years or so. And to the best of my knowledge, it hasn't affected any of the geothermal production on the river. So I don't necessarily see that there is a relationship between the two.
Yeah, I've heard people say if you take steam out for geothermal, then you keep re-injecting the brine, then you get more solids dissolved, and after a while the rock's not permeable anymore. Do you think that happens?
I don't really know. I mean, I know that they have been injecting in some of the wells for quite a long time. And I know in other hydrothermal systems, reinjection of fluids has either been done or not been done or partially been done. And potentially you can have an effect on either the formation characteristics, or on the fluid compositions. But sort of one of the advantages that PGV's reinjection has over some of the others is that essentially everything that comes up is going back down. If you go, this is something that I guess is not widely known, but in Iraq, they didn't do injection. They were just dumping the geothermal effluent into the river and suffered serious subsidence of the ground surface. And so it's one of these things that, by not doing it, there is also very serious potential. I'm not sure that necessarily applies to the East Rift Zone because the geology is fundamentally different from what they have in New Zealand. But at least in the New Zealand case, there is an example where lack of reinjection did lead to adverse surface consequences. And the same is also true of the geysers geothermal field, where in Northern California, they pulled, I don't know what the number is, but it's in the million pound a year of steam out of the geothermal resource without putting them back. and without re-injecting at all. And they severely depleted the resource. And what they eventually did was, they kind of had a collaboration of interests with Santa Rosa. Santa Rosa had been, in the bad old days, dumping their wastewater into the Russian River. And they were forbidden to continue that practice. And so what they did was they made an arrangement with the geysers geothermal field to take the treated wastewater, pipe it over the hill, and use it as makeup water, injecting it into the geysers geothermal field. And it was very successful. It actually replenished the steam source in the geysers field. Yes, sir.
Has anybody made an estimate or a decent estimate of how much energy is available in the East Rift Zone? If we decide to exploit it fully?
Estimates have been made, but they're, the politest term I could use is they're speculative. The recoverable heat within the rift zone is substantial. As you probably know, I mean, one of the boreholes drilled down there, they had actually encountered molten magma at 2 kilometers or 2.5 kilometers down. So there's lots and lots of heat down there. The question really hinges on whether the heat can be efficiently extracted, whether there's permeability there that will allow them to recover that heat, or allow anyone to recover that heat. And again, that's one of those questions that we don't yet have an answer to. Yes, sir.
Say your studies on the older parts of Hawaii Island and on Maui and Oahu do show a heat source. Is there the technology available to extract it? Because I would assume it would be at a deeper level. And would that technology be similar to what's being used on the mainland right now?
Well, I guess I can't give you a definitive answer on that. It really will depend on if it is deeper, how much deeper it is. And certainly that there is technology available that you can drill wells 20,000 feet deep if you have deep enough pockets. But it then becomes a question, is it economically viable? And that really has to be looked at. If the resource is instead of being 6,000 or 8,000 feet down, is 15,000 to 20,000 feet down, say on Oahu, then it's going to be really difficult to economically extract that heat. And ultimately, whoever is going to try to extract that heat hopes to get back the money they put into it. And that really is the question. But the technology certainly exists. I mean, there are some very deep holes that are drilled in the oil and gas industry.
And on the continental USA, where they're doing that enhanced geothermal, aren't they already going really deep? Because the idea is the farther you go into the Earth's core is hot, so you do it, and so they use a method called fracking. And
they do the fracturing really has been researched for a number of years, and in the early days, this was in I believe it was in Mexico. It really was more of a matter of whether you can get water into this, what they referred to at the time as hot dry rock, and whether you can circulate fluid in and extract that heat in an economically viable way. And that economically viable way is the operative term on these things. Because yes, as you go deeper, you get higher temperature, but as you go deeper, the costs of getting at that heat increase. If they increase faster than your temperature does, then you're losing ground. And they do increase drastically as you go deeper. So I think that's often been forgotten. But yeah, there may be a vast store of heat down there, but if you can't economically recover it, then, you know, who's there?
I think a lot of people have to get back to work, so let's take maybe one or two more questions, and then if people want to stay, I don't know if
Sure,
John's
I'm happy
willing
to
to
stay
stick
for a while.
around.
Sure. Yes, sir.
Given the governor's proposals to pull 500 megawatts out of the Pune Strip and ship it to Oahu, whereas the volcano guys say that the total resource is about 100 megawatts, would you comment on that?
I would not concur that the resource is 100 megawatts. I think it's probably, I mean, it may be 100 megawatts on their lease, on the PGV lease, but there's a lot of rips on there. But really, part of the purpose of this project is to provide alternatives to the East Rift Zone as potential resources. The ideal alternative, of course, is if we could find a resource on Oahu.
Since we live down there, could you comment on the health effects?
I'll give you my opinion. I suspect I've inhaled about 20 times more hydrogen sulfide than any resident of Nowelo St has. And I haven't noticed an adverse health effect. Now that's maybe a wiseacre response, but a recent study that was done in Rotorua, where concentrations in the city routinely exceed 5,000 parts per billion for extended periods of time. They did an epidemiological study. The gentleman leading that study's name is Bates. He's from Stanford. He teamed up with public health folks in Rotorua, and he was not able to find a significant adverse health impact from those routine high hydrogen sulfide concentrations. And I visited Rotorua, and there's lots of H2S now. Yes, ma'am.
Yeah, I was wondering, is the state or the DOE ever going to think about seeking technical assistance from Iceland, as they are the world leaders in geothermal technology, and they have a very similar geologic environment as we do, since they are a hotspot and we are a hotspot. So I was just wondering. And as you mentioned with New Zealand, they've helped New Zealand and Singapore and the Philippines and so on and so forth.
Some of our former students from the village are Icelanders.
Yeah. So.
But certainly we're in communication with them, and they actually contacted me recently about the work that I did on at the old HTPA pool on the fluid rejection. To get information on it. So we're in communication, and you know, they're very interested in sort of how things are going
and
here.
They took their brine and made it into a spa called
Right.
the Blue Lagoon.
Yep, oh yeah. Great place. I went there. It cost me, 10 years ago, it cost you about $15 to go soak in the geothermal brine. Yes, sir.
Okay, last question.
The Bates study that you're referring to, is it the Bates study that has just been released?
Yeah.
I think I read it, and I think it said that exposures that they considered were up to 64 ppb and only limited itself to asthma. It didn't talk about other health effects.
Right. Well, it was.
So
that was
maybe it didn't quite
average.
say what.
That was sort of the long-term integrated average, and that is that's a different way of measuring what their exposure was.
It didn't limit itself to sponsoring asthma.
No.
The study talked about asthma.
Right.
And whether it caused asthma, not whether it caused more severe asthma, nor did it talk about any other.
My recollection of what their conclusion was is that they also saw lower rates of reported asthma response within sort of that high exposure group than they did outside of that area. So what they were speculating was that there may be actually a suppression of the asthma response. And that's that's the first, and this is, as far as I'm concerned, and their work going on is really one of the most extensive studies of public health exposure to H2S that has ever been done. They've really gone to great lengths to document what the integrated exposure is by segregating sort of exposure at work and exposure at home. And they've got, I think, 16 or 1,700 participants in the study, which is statistically a significant number of people. And this is the first of what I expect to be a number of papers.
Yeah, but it really didn't measure effects up to 5,000 ppb.
Well,
And it didn't really measure anything except asthma. At least that's what they said in the summary.
if you look at the map, though, of the hydrogen sulfide concentrations, there are places within Rotorua City where the concentrations do exceed 5 parts per million on a routine basis.
I'm just saying, I don't know that. I've never been there. I just read this. I had one additional question.
Well, let's let everybody else leave, and I'll be happy to.
Nelson, how are you? Good to see you, mister.
We don't really have complete detail on ground geology, we've got the survey, which is the term that they use is the direction parallel to the ground surface and the dip, and that's right, it could be tilting and dipping down to the north, or it could be dipping down to the south. And we don't have, but it is mostly the rip zone is generally considered to be sort of these and essentially they've been described as the main blank
About whether the resource was losing heat, you said something about a study
Well, I guess what I was responding to was the idea that the reason that may very well be true. What I do know, this is back from the early 90s, That's what I think is
Are you gonna release the data by item, which takes the big item like first, or are you gonna hold back until qualified? When, I missed it, when did you say the big item?
Well, okay, we're gonna be,
And then you release something kind of like.
I don't see any benefit in again, as I said, basically, it's the need to access.
You would think they would be begging you to come to their.
Well, on the one hand, yes, but on the other hand, they want to keep that information to themselves.
But it comes at a cost.
And I mean, that's, my stink is, well,
I don't see why they would be afraid, because if they did not, if they were area unproductive, they're sitting on top of the cat. They don't say, you is not you. So to me, that's sort of a false thing where we got to withhold data from someone.
this is what we do. To your question, though, I mean, the only accurate answer is, hey, I'm gonna deal with the land. Because they have, access control. If they choose not to have that data.
At the same time, you're not doing a really fine gradation study, you could jump property and still get a reasonable picture of what's happening.
Okay.
So is it public information?
Public property would be told this. Private property, I get a
So there wouldn't even be a record that you need.
Oh.
They could keep the location.
I'll be there, and intrusive,
I'm still
within this area, I mean, what I would like to do is share it, but look, if I don't release the data per se, let me at least release interpret images of what we're seeing.
So my question is, would there be some record of what property is served?
I don't see why. Yeah, I mean, and what I have to do is do these, really broad, I don't have any fixed on some of the groups. Some are in the abstract. I'm gonna have to find it, before we can assess the research. So, sort of do sort of transect response, see sort of how it evolves.
No, because they, what they did is they bulldozed it all, it's open. Well, no, the buildings are still there.
The thing that is running drives
MIT study in 2007.
And anyway,
The talk
that is
so seems like you're not yet convinced that's an economically viable. And you
Well, again, I like to try to base my business on data.
Money geothermal companies jumping at this, governor, everybody else who created your statements, one of those lines is perhaps to slow this down.
Well, it's to, try to temper your enthusiasm and a little bit of data would be a good idea. That would be helpful. I mean, that's what I said, and I mean, I've had people, from DBED ask me, look, I don't have enough data to say whether this is a good idea or a bad idea. This area is a good idea or a bad idea.
But we've got a governor who wants to pass
They wanted to fast track it 30 years ago. And
I see another I have read Kate Dover's book and Dr. Levine, and I have to say, he almost said that H2S is good for you. The data I have says it causes birth defects that have a higher resilience. It's 30 times more toxic.
I don't buy it. Sorry. I mean, I work with these geothermal fluids. I work in the laboratory with geothermal fluids, but very high concentration.
Okay, we're showing examples down there. If I use it, maybe brain damage.
Wineries produce more than 100%. Two, sometimes you find that
I don't know.
basically, that's why I like the what we were saying. This is an area where we have natural exposure, there is no predisposition why the people living in those whether it's good or indifferent, it's there, it is. And so there's none of the inherent biases in any study where they've got an unwanted land use here. So that's why I like that. Basically, you've got a population that's going to store routinely exposed to high concentration of solar power. You go into that city, okay, nighttime.
You don't need to leave.
You get nighttime emergence there. Early morning, guys have been there and measured 5 parts per million H2S in the city.
All right, see you all.
It's sitting in a caldera.
Yeah.
It's a huge caldera. The city is actually located over. It's bizarre. If you walk down the sidewalk and there's.
Excuse me, I have to go back to work. Thank you so much, Don. Appreciate it.
Bob.
But you go down the sidewalk and where the sidewalk abuts the side of the building, it's little cracks with sulfur crystals growing from steam naturally emanating from the ground. So I mean, it's there's sulfur dioxide and hydrogen sulfide, throughout the city.
Hillary argument was, this is does it do? It says the area is rather poorly converted to hydro.
But of course, that's not how the chemistry works in the model. I know. But there are studies on H2S. Well, okay, there are studies of H2S actually being generated in the sites.
Oh, yeah? So the
Now, that's long-term exposure, lifetime exposure. Okay? That's number one. Number two, you got it.
Well, that's.
And lifetime exposure. So it's hard for me to accept the thesis.
My friend Adrian was 400 yards from your well. Pretty slow well. He said, he's sitting on his porch and minding his own business. The next thing he knew, he was wondering why the horizon was just going to burn. And then he said he felt something on his shoulder. He tried to brush it off. And his memory loss, headaches, the whole 9 yards. You know, he was 400 yards away.
With PGVs, just hydrogen sulfide.
Yeah, there's radon, cadmium, arsenic.
It's not real prevalent checking.
How about the radon? 200,000 picocuries per liter, but the rest of it is greater than 4.
And you look at the data, I calculated what the concentration of radon is. That's one of the studies that I spent a lot of my years making, looking at radon activity. And radon activity on the ground is naturally for and the 2,000 picocuries is per liter of condensed steam. And so if you take that steam and volatilize it into, take it that water and volatilize it into steam, the concentration per cubic meter Right. Meter is like 44 moles. So you're talking about a huge increase in volume or decrease in the case may be when you condense that steam. And additional reality is that, Steve, you're studying it. I'm looking at radon and soil gas and transport radon. One of the things I find that's what incidentally it's not the radon's harm. The radon is not the issue. It is not what causes it's the radon byproducts. And basically, if radon goes to polonium, to lead, to bismuth, back to polonium, and so it's got a sequence. But see, the polonium, again, what the issue is with radon, okay, is if you're in an energy efficient process where you have minimal air exchange, you have the air and the radon trapped inside. What happens is the radon decays to the daughter products. And radon is naturally a gas. The daughter products are all solids. And so the sequence of events will have the played out in dust or actually smoke. You inhale that dust particle, smoke particle, and what it does is deposit
I'm getting ready to buy another.
in the lung. And then it continues to decay. So that really is ultimately the source of the increase. It's not inhaled inhalation rate itself, it's from inhalation sticking.
Because that's my market.
Back to the MIT study, they recommended, the study group recommended that the federal government encourage exploration through the enhanced geothermal systems by investing money in grants.
It's hard to.
Risk-free loans to companies. We don't know much. We have an order of magnitude with how much of that type of money is currently left.
I haven't even looked at
The top stuff is
anything or what they're talking about there. again, I mean, the MIT guys are smart, but how long do they spend on it?
So it may apply other places.
It may be more applicable.
If we have so little trouble lava, instructors, so they.
So anyway, I looked up.
Fracking doesn't bother me. Right, but you're dealing with very, very different conditions. You're dealing with, okay, why is it messing up the groundwater?
Seems to be messing up the ground, sorry, because the current geothermal seems to be contaminating green lake over
Green Lake is actually not connected to the hydrologic system within the district.
All right.
Sample the
Enjoy
Green Lake
Hawaii.
30 years ago, and what I concluded was that it was basically a crater-bound system. The chemistry, very striking contrast from the chemistry of the groundwater in East Ripon. And one of the most striking characteristics is that the Green Lake water has high magnesium. And the magnesium is being extracted from the ash, and that big ash. Yeah. And one of the characteristics of the geothermal water is that it has anomalously low magnesium.
Okay, that's good.
So,
thank you.
so
many details.
Yeah.
That's why I'm asking.
Right. No, I mean, this is why I get a little frustrated, because I mean, we did all this stuff 30 years ago, and the data is available. If anybody's interested in, I mean, I'm actually in the process of getting all this stuff online. Good. Basically, all you got to do is go to.
That's GS friendly.
No, it's University of Hawaii Library. You go to. They've got a program underway right now to digitize old documents, and one sort of set of what do they call it? One collection, I guess, is called eVols, and the other is called Scholar Space. And Scholar Space is dominantly documents that have been generated by University of Hawaii students and staff. So all of the graduate theses are there.
Scholar Space.
Scholar Space. Yeah. And we've got over 1,000 documents that we put up there. These are the old geothermal studies, the work that was done by the College of Engineering, all of those that I could, lay hands on. We scanned into searchable PDF documents, and that site gets a workout. They send me monthly statistics on, and one of them I think had like 850 hits last month. So people are going to that space and downloading those documents, but it's all that old data. Some of which I suspect only existed in my closet. And everybody that I'm kind of last man standing from the early geothermal stuff. And I was
what's happened to Goddard?
Assistant researcher.
Happen to know what's happened to Goddard?
He was from California.
Yeah.
He came in, and I haven't interacted with him. He has been sort of
I know.
president of the city.
Oh, Shannon's sure. Not here yet.
No.
Would you be willing to continue on your fracking?
Okay, well, fracking can be done at multiple different scales. And, I guess I should preface everything by saying I'm not advocating fracking, but I'm not advocating banning it either. Okay. Because I don't think there's enough data. Like I said, I like to base opinions on some real data. And the experience on the mainland is in just extraordinarily different geologic environment. The purpose of the fracturing is very, very different. Because what they're trying to do is get, very broad scale, distribution of cracks to try to mobilize, gas and liquid phase hydrocarbons.
Sure.
And Hawaii's rocks, number one, don't have hydrocarbons.
Right, okay. I just thought it was an obvious risk to groundwater.
Why would it be an obvious risk to groundwater?
Because it's permanent, like you said, substructure is all broken up, you can check it out in, and it transports to the rock.
But the reason that you inject the water to generate fractures is to actually open it up.
Yeah.
I mean, some rocks are highly fractured.
Oh, I see.
Other rocks are not.
It's limited by the permeability around where you're.
Right,
Okay.
right.
That's a good point.
Yeah.
And in
So-
fracking here, would it be just with water, or would it be with any other? The chemical
Everything
things is
I've
like-
seen, right, yeah. Everything I've seen is that in the work that has been done is water and sand.
Mm.
And I've seen some.
Not the case there though, right?
Right, there,
Mainland,
there's a
they're
bunch
using
of
lots
other
of
stuff,
chemicals.
I have no idea what
Surfactants
they've
and
got.
for it.
Right.
Yeah.
They won't even tell you it's stuff for it.
But I mean, but again, I mean, I'm neither advocating nor, saying that we should prohibit it. I think, it's like any other activity that you have to look at it very carefully and see, what is the risk and what are the potential benefits. And at this point, I'm not convinced of either that, we could, go in and take a thermal system that was impermeable and make it economic by inducing fractures in it.
Has it even been done here? I mean,
Never been done.
Don't even have a good example.
Just asking, it's been suggested that the reinjection wells are doing a certain fraction. Is that right?
I honestly, I don't have any way to know.
I mean, some say it goes right back into the resource where it came from, others say it goes into a slightly different formation.
It may, yeah, I mean, what I have heard is that they injected somewhat deeper than the fluids, than where they're pulling the fluids out of. But, that, I don't see that that's necessarily a bad thing. In some of these geothermal production systems that have done reinjection, one of the biggest threats is that they put it into a permeable formation that immediately returns back to the production well, and that just kills it, just cools it right down.
There was concern some years ago about quake, and there were reports of what they call swarm quakes in North Valley.
Right.
Attributed to the geothermal. Don't know.
This is the problem,
I mean, there's
honestly.
at least a question of whether these things are going to induce quake.
It's certainly a legitimate question, but what I don't like is that, everything that happens gets attributed to what's being done at the geothermal plant, regardless of, how far distant it is from, whatever is happening at the geothermal plant. And I mean, that's not well, it's not a rational.
Of course.
No, I mean, if there's gonna be cause and effect, you wanna have, some rational way to generate the effect from the cause.
Speaking of which, would you think there's any connection with the fish dying at Komohana? And then a friend told me at Hawaiian Acres, this mud bubble came up in her fish pond and some of the fish died. But is the PGV area connected in any way to those two areas?
There certainly is not a close connection between them. You would have to look, I mean, as I mentioned, you've got the dike system and the fabric of the dike system is such that, okay, fluids, one could argue, and again, I don't know this for a fact, one could argue that fluids that are injected here are going to spread along the strike of the root zone. But again, you look at the injection fluids, and then you look at the natural discharge of hydrothermal fluids along the root zone. And, that discharge has been going on,
Could we just dump some fluorescein in there and find out?
Like some dye?
Yeah, where's he dye? You can detect it at parts per billion.
Right, you probably wouldn't be able to detect anything for a couple of reasons. Because, okay, again, you're injecting it into a high temperature system, and the dye is just going like that.
Right, good point.
That'd be a pretty scary guy, probably.
Yeah, but the other reason though is that one of my cohorts has been looking at wastewater injection wells now, and they, I think they came only 400 feet down, and there was some suggestion that the wastewater was coming back to the surface, and they injected fluorescein months before they saw any evidence, and just 100 meters or more.
Wow.
Yeah, and here they're injected.
Well, that's good to know.
2,000 meters.
Maybe you could clear up another thing that I've heard it about 4 times. I have no idea the problem. But they're claiming that the initial drilling on Nowelo St land was right where Hilo is.
No.
And I've heard the story that supposedly the lava came up there and that the exploratory well may have had something to do with Hilo.
You're making my point.
No, I understand. I wanted to, but you were around, so
I was around.
So I'm asking.
Hilo is, a couple of kilometers at least away from where they did the
That's a
drill.
good point. Oh, okay. Some said it was right on the point. So.
Well, this is the thing, there's this active
Trying to
movement
find out
on
the
there's myth-making that goes on in Boone, that, people generate these stories just with great names, and they just have no business in knowing it, and it's really frustrating.
I'm excited to do, I'm trying my best to do due diligence.
Yeah.
But I do know people that apparently have gotten pretty sick from this. I grant it may be sporadic, all that, but.
Well, one of the other things that I was going to mention, to me, it was kind of a telling study. Let me turn these off. Something that stuck with me was a study that was done. It's been quite a few years ago, because I know I looked at it back in the 80s. But there was a rat study where they exposed rats to varying levels of hydrogen sulfide. It was a laboratory study. And they exposed one set of rats to 80% of the lethal dose, 5 days a week, 8 hours a day. And for weeks at a stretch. And there was no difference in weight gain, no difference in activity, no difference in anything in those rats that they could find at 80% of the lethal dose.
But did they die?
No, they killed them.
But they were the same rats.
That's a criminal study. Is there any chance at all you can track that one?
Oh, jeez. I mean, it probably would, I don't know, it might have been.
I mean, I see your point in a sense, are eukaryotic cells evolved from the smoker vents?
Well,
So we may have detoxification in there.
Right, exactly. And I mean, that's, okay, my own story was that, I would be working at the old HGPA plant, and one of the jobs that I was doing was I was tracking the hydrogen sulfide concentration in the steam. And so I would have, like a month's worth of samples of steam condensate. I'd sit there precipitating or titrating this stuff. And as part of the analysis process, I'm taking a significant sample of this steam condensate with H2S and volatilizing H2S. And, the one thing I can say is it didn't have many visitors or repeat visitors. Because people would come into the lab and say, no way, I'm out of here. Okay. I'd go back home and I'd still be sweating sulfur 2 days later. I mean,
Saturated with it.
yeah. I mean, I inhaled lots and lots of H2O. And I was actually, I mean, I was the resident
A
chemist.
wide range of sensitivity going on here. I mean, certainly.
But the Rotorua study, that says a lot, right? I mean, that's pretty telling. Unless those people are, you know, maybe there's a genetic modification going on there.
Well, I mean, the Bates even looked at, you know, whether, you know, there was sort of self-selection, whether people, you know, had.
The Maoris are all thick around there.
Yeah, oh yeah, yeah. But, you know, he was looking at whether they basically took themselves out of the environment because they hated, you know, they didn't like the H2S. But he said that, you know, he did not find any anomalous, and this is my recollection, any anomalous distribution in ages. You know, there were long-time residents there, and there was no kind of distribution of only people who were sort of relative newcomers that were hanging around, and the old-timers had left because they got, you know, sick or died or whatever. And I don't, you know, the one study that's been published is not by any means the end of it. He, you know, I've communicated with him by email a couple of times, and he, you know, he's got probably half a dozen more papers to do.
I'll definitely read it, I'll just say, you know, it seems to seriously contradict a whole bunch of stuff that I've already read.
Yeah. And, you know, and even in Kilmer's stuff, and then, you know, some of these other studies.
You know, the data was quite senior and seemed to be pretty wide, so, you know, I don't think, I got that they were just lying.
Well, you know, okay, but the thing is that there is a self-selection bias, and if Legator study is the one I'm thinking of, because of
Well, yeah, it was only a preliminary survey.
Right, and it was, you know, the participants were, you know, sort of self-selected, who were pissed off about geothermal being in their backyard. And so that's, you know, not in any way, shape, or form an unbiased study.
I was hoping for something that would follow on, but DOH has been completely silent.
Well, see, DOH did a study, though. DOH did a study back in the 80s, and that's available on that site.
My understanding was they excluded anybody who complained about the geothermal from their study.
I'm not sure I believe that.
Oh, well, that was said.
That is true. I know that for a fact.
You
So, I mean,
They
so that's
absolutely
bias
excluded
in
people
the
from the
I'm just
study.
pointing out that's
Oh,
bias in
Oh,
the
for
data.
sure, yeah.
'Cause
They were
didn't-
in this
they-
room, some of them, so
Oh, like the Don fellow, or?
I won't say who, but I know for sure. I heard it from more than one source and more than one instance. Yeah.
Well, and
some
it
of the
maybe
people in
was
this
partly
room
because they
are
didn't want
fairly
the
noted
bias, huh?
for being very
Yeah.
flexible with the truth.
How can a blood test be biased?
Mhm.
How can an O2 sat be biased? I have a hard time thinking that was a good scientific study if bias was considered.
Well,
Yeah?
whether they did a study.
Yeah, and I
20 years
suppose all
ago,
the people that are
nobody's
nearby,
yet to
they're
show up
gonna be the
in
ones that are more
meetings.
impacted.
Even when they were invited.
So that they, yeah,
Since
they're.
they're the
And
results
studying it in a
of
lab for a
the
couple
agency
hours or a day or a week is
for
not the
these
same
kind of
as
studies.
living there for
I'm just
25
appalled.
years. That's what they're
It's been 30
saying.
years and they've done that.
I don't know.
Well,
I would like to see an unbiased scientific study tell us about that.
Yeah.
And the
16
fact is,
years.
because we have an unbiased one on the books, we can't get a proper one.
Why is that?
Because that's the answer. Well, we had one
Because gases do
25
not,
years ago.
in and of themselves,
It's also a different situation now because it's been there for 20 or 30 years.
you wouldn't be able to.
You know, it's different as a startup. It's a completely different
CO2
situation
is not in and
than
of
what it is
itself.
now.
Yeah, I guess
Do you
that's
drive a
true,
30-year-old
as long as
car?
the thermal mixing is enough to
No.
shut it up. Yeah.
But again, this is part of sort of this fanciful set of allegations that whatever work that was done that doesn't agree with the predisposition of the residents has to be biased.
Okay. Well, one time at about 3 in the morning, I was down on Nowelo, near the plant. And, I know we were walking down Nowelo, and there was some background light stuff. And you could see this tube of stuff. It was about, I don't know, on the order of 30 feet across, tube that went up like that. And you could see it was flowing towards the puddle, more or less. And there was a distinct refractive index change or something. It glistened in weird looking. And you could just about, there was a pretty defined zone. So you could almost walk up and touch the boundary. I mean, there's some fall off, of course. But I was just wondering, what the hell is that big tube of stuff going down the hole? Like, what is it?
I don't know. Let's
Something
see.
being dumped from the plant late at night, and it certainly had its own cohesion. It had a different
Well,
density and it held together.
at night you get a ground inversion where the air near the ground cools off, and basically, this is something that, again, was part of the study that was done, came out of the studies that were done in the seventies and eighties, that you get this ground level inversion that actually grows, overnight, during the night. And so what it does, and it is quite true, that it will trap emissions in that inversion during the night.
That could be what I was saying. But it looked like a sort of well-defined tube about 30 feet. I don't know, it could have been, it's hard to say, of course. It wasn't ground up.
But I mean, we can see that, and it happens very commonly because the ground radiates heat away.
Sure.
And essentially you get this ground level inversion where the air will cool off and become more dense than the air overlying. And so what was seen in some of the studies was that the H2S would get trapped. What H2S emissions was, this wasn't from the PGV plant, this was from the HEPA plant. And basically because they were warmer than the air down in the ground, they would be up at elevation. And when sort of the sun hit the ground and heated the ground, there would be an overturn. And at a certain time of the day, you'd see a little spike in the H2S as that mixing caused an overturn of the inversion like that. And it led to all kinds of strange stuff because there was a phenomenon down there where on Komohana Road, you could hear traffic on the whole Komohana Road. There was basically that ground inversion. Sound from the road would come up and then bounce back down. Yeah. So you get these really weird audio effects as well due to that, again, that density difference in the
I have one more historical question. Just again, stories I've heard, I got here after the blowout, just a collecting story. They said in the early days of the geothermal, it was considered that there would be so much power here that it would be the expression of 2 gigameters supposedly came up. Is that real or never?
pure fancy.
Okay.
No,
In the early days, people had stars in their eyes about what they could produce.
Well, I mean, it's what they could produce, and I mean, you get, again, the sort of the non-technical people letting their enthusiasm get ahead of reality. I mean, the reality is that
At least at times it was attributed to you, so that's partly why I'm asking. Again, you're right, there are all kinds of stories. I mean, just, forgive me for even asking, but I just want to get things
I know what wells cost.
Yeah.
If you're drilling a geothermal well, I mean, this is one of the difficulties with geothermal is that you have very high capital costs, and whereas in electric utility, they build a power plant as soon as it's done, and the DOH signs off on the permits. They turn on the oil, turn on the switch, and they're generating money.
Right.
Okay, with the geothermal plant, not only are you, in effect, and it would be the same situation if the electric utility had to go to Saudi Arabia and drill the oil wells and prove those out, and then
dry wells.
Right, and then come over and build their power plant, and that's not the way it works.
Right.
So if you're going to develop a geothermal resource, you've got to basically prove up the resource with sufficient reliability to justify building a power plant.
Right.
And each of those wells, $8, $10, $12 million a pop. Yeah, they're not cheap. And so you're holding the bag on that until you can get your power plant designed, built, and operation.
It's about 20-year-old data that I was told the current PG&E thing had about 200 million invested for 30 megawatts worth of power, which made it like 6 times the nuclear plant in terms of capital investment per kilowatt.
Again, I take that number with a truckload of salt too.
Well, I figure you might know the number.
You know, I'm not that close to the geothermal bench.
Okay.
They don't share their secrets with me at all.
All right.
They ask a lot of questions, but they don't get a lot of answers.
Volunteer right now. I have a totally unrelated, and that is I guess there's like around 2,000 miles of lava tubes that are mapped within the island on the Big Island, that are above sea level. And I was just curious, do they form at all under sea level? I would think not, but I've never really heard it talked about.
I would say that there would be they would have to be extraordinarily big. Again, the reason I say that is that, okay, you've got cooling, but you got to look at how a lava tube forms.
Yeah.
And you've got this long leg flow. It basically crusts over. And
lava in the ocean just kind of explodes.
Right. Yeah, very few lava flows can actually make it across the land-ocean interface and remain coherent. And,
unlikely then, but there probably would be some that have sunk.
Oh yeah, absolutely.
Yeah,
we know that they're there. Yeah.
Now, when you were talking about the land level sinking too, the pictures you showed, were those like significant drops over time? Like what kind of drops in depth, say?
You have this ongoing subsidence. Okay, the Hilo area is subsiding at about 2.5 millimeters a year, and that's sort of the long-term average subsidy. You also have faulting similar that goes on down on the south flank of the Kilauea, where you've got that episodic faulting, you've got the marine faults. But where we drilled here next to the airport, it had subsided by over 1,000 meters from the first subaerial lava flow.
And that's from the weight.
The jury's out on that. I got sort of my own opinion. Some of it is this phenomenon they call lithospheric flexure, where the weight of the mountain pushes down on the tectonic plate. But in the drilling, what we found was that when we drilled into the broken up formation, the stuff that was generated by lava flows going into the ocean, we found sort of the shallowest portion of that material was very open and lots of pore volume in it. And as we got deeper, it got more and more compacted, and it had lost about 30% of its volume.
Oh.
And so I suspect that what it is, the substance that we see is partly compaction, and partly with the spheric flexure. So you've got both of those processes going.
Which you wouldn't get that necessarily on main flows that are above the surface, but
right,
where
the
the
stuff underneath. See, this has been, I don't know that I made it really well, is that, I think a huge percentage of the island is made up of stuff that's generated by flows going into the ocean. Because when the volcano first breaks the surface, it's a very steep-sided edifice. And so at that point, then it starts generating this broken, what we call haloclastite material. And that sort of broadens out, and only when that is stable enough to sustain a flow on top of it. And that takes a while, as you see down there at Puna, because you build up these benches, and then those benches just collapse into the ocean. So a significant fraction of sort of the basement of the island is made up of this fragmental material.
Now, is that what maybe causes some of those significant earthquakes?
I don't think so. What we found was that they start out, as I say, very open and porous and lots of water flow through them. But over time, they become compacted and cemented back together. From the weight and from water circulation through the system, and you get low temperature mineralization, the clay formation that sort of moves things back together. But I think that's a significant fraction of the deeper part of the island, is this broken up stuff. And so that's why you see that.
So there's gotta be a layer of that all along as
Yeah.
it's hitting the ocean, right?
Right,
It's
exactly.
there everywhere, really.
I had read that there's, kind of a shelf that goes out over the water, maybe 15 miles.
Under the water. And in some places, yes, be good, but that shelf and where the slope breaks is actually the extent of the subaerial portion of the island as it grew, but has now subsided. Because that steep slope is in effect the angle of repose of the rubble that's generated out of the lagoon.
You probably know about the critical angles
Oh,
of
yeah.
slump stuff.
Yeah,
Do we fit that? They do it with sand, they keep
Yeah.
adding more sand,
Right,
and eventually
right.
the thing will slump. There's all
Um,
these gas math things that they do that.
yeah.
I'd be curious if a volcano.
It must be, because it's mostly stable. But, you know, we don't really know whether it's volcanic activity. I mean, there's speculation abounds, that, you know, it's volcanic phenomenon that generates these major landslide events. It's also been speculated that we see these landslide events after ice ages. At the ends of ice ages, when sea level is at its lowest and the unsupported slope is the longest.
The water kind of How long before your well that you've got up on saddle, do you have any idea how much longer it'll be before they get down to the area that you suspect has the water in it? I mean,
I wish I knew.
there's you're saying you suspect it's like maybe up as high as
Yeah.
3,000 feet, 3,000 meters, you said.
3,000 feet, 1,000 meters.
What I'm probably gonna
That'd
do
be a
is put
huge
the
amount of
camera
water.
up first.
Yeah.
But yeah, the battery
And
died on that
it's, the drilling has been just way more difficult than we anticipated.
But in theory, how long before that well gets it down?
Well, I mean, it could be another month.
Public meeting. Oh, I didn't wanna be shy. Yeah.
Things go well.
That'll be interesting.
Yeah.
Thank you.
Good, yeah, my pleasure. Yeah, my pleasure.
It's not gonna come out well.
I'm like, it's gonna be like super intense.